In the last lecture, we looked at radiative equilibrium. In the presence of a gas which is absorbing, and we solved this problem between two parallel plates. And we first looked at the exponential kernel approximation and showed that this gives fairly accurate results for both radiative flux as well as the temperature distribution. Then we looked at the optically thick limit, and along with that we applied the radiation slip conditions, and again we obtain results which are consistent with the kernel approximation and the accurate numerical solution. And the result we got was that radiative flux was equal to one plus 3/4. So, this result is a very useful result. This is between black plates, and this shows that where K0 is the absorption coefficient times the length of the gap between the two plates, and this shows that in the optically thick limit this quantity becomes very large and the flux tends to 0, and in the optically thin limit this quantity is 0. So, we are back to the original result we had obtained earlier for heat transfer between two plates without any absorbing gas in between. Now, today we want to extend the result between two parallel plates, which are not black. So, let us see how we extend it. If you recall, the result for heat transfer between two plates which is not black is that Q of R is B1 minus B2 So, this is general result obtained already in the kernel approximation. Now, we want to now write this explicitly in terms of T1, T2, the two temperatures and the emissivity of the surfaces. To do that, we recognize the following: radiative heat flux at the bottom wall is radiosity minus emission from the bottom surface minus 2/3 and similarly at the top wall these are from the flux condition. Now, I want to remind you that in radiation heat transfer, we cannot assert that the temperature of the gas next to the wall will be same as the gas temperature, as the wall temperature. That is, we must permit the fact that there is a slip between the gas temperature and the wall temperature. This is not normally invoked in conduction or convection heat transfer studies. In radiation, we have to invoke it, because unless it is in the optically thick regime, generally there is a temperature difference between the gas layers next to the wall and the wall temperature. Although the temperature is not continuous between the gas and the wall, fluxes are continuous. Fluxes are continuous because a discontinuous flux implies a violation of the first law of thermodynamics, because if a flux is discontinuous, then the divergence of the flux will become infinity. So, for example, in our case will be equal to infinity if f is not continuous. Therefore, we always invoke the continuity of flux, and this result here is from this condition. Now, we also know that under radiative equilibrium, this quantity is related to the radiative flux. So, we can rewrite this above expression as QR. And we know that the from the previous equation that this is nothing but this term can be written as and therefore, we get this result that radiative flux 1 plus 3 to the 4th. This was already obtained by current approximation. We are rederiving it for the thick limit. Question is, what is B1 and B2? Now, this if you recall from the radiative transient closures, flux on the cage surface is epsilon k by 1 minus epsilon k. So, this is derived as a gender relationship between flux, radiosity and the wall temperature. We use this result for the two walls, which is multiplied this way. So, we can write this as B k equal to sigma T k to the power of 4 minus 1 minus epsilon k q k. So, this is applied to the two walls. So, one result is and the second result is so this should be written as Q of this is bottom wall, top wall. And if you recall the fact in relation to these two results which we have in front, we now calculate what is B1 minus B2 from this equation. And this comes out as plus 1 by epsilon 2 minus 1. Now, here we use the fact that under radiative equilibrium Q of 0 is Q of kappa 0. Now, if you use the result that B1 and B2 is nothing but QR into or Q0 into 1 plus 3/4 kappa 0 is equal to sigma minus Q0 So now we take all the Q0 to one side and you can see that one will disappear, another one will remain. So, we will have Q0 into 1 plus epsilon 1 plus 1 plus epsilon 2 minus 1 from these terms plus kappa 0 equals. So, we get the final result, which is that Q0 or QR in general, because Q is a constant across the. So, QR finally, which is same as Q of 0 equal to Q of kappa 0 is sigma Now, this result is a general result, and notice that when kappa 0 goes to 0, that is the thin limit, we recover the old result for radiative heat transfer between parallel plates. And notice that in the limit as kappa 0 becomes very large, if we neglect these terms, then the emissivity of the two walls becomes irrelevant. So, in the optically thick limit, the gas hardly sees the two walls, and hence the emissivity of the two walls is totally irrelevant. So, this result is a nice result, clearly showing when should we include gas radiation. For example, if you look at the insulation used commonly made of aluminized mylar reflective layers, hundreds of them, the emissivity of these surfaces may be 0.01. You can see that this will add up to around 200. So, unless the radiation optical depth of the gases between the reflecting layers is very large, this term is not important. So, the gas radiation becomes important only if the two walls are black, and so this becomes 1, and this quantity, let us say, is as high as 10 or so. Otherwise, the gas between two parallel plates is not important if the emissivity of the two walls is very, very small. And this is best understood in terms of resonance analogy. So, you can see clearly that there are two surfaces. You can call this now a gas resistance. It also has geometric resistance built into it. This is surface resistance. This is also a surface resistance. So, you see that if the optical thickness of the layer is very, very large, then this dominates, and these two are not important. On the other hand, if the emissivities are very, very small, the surface resistance dominates. So, the geometric factor and the gas resistance is not relevant. So, this kind of electrical knowledge is useful to understand which particular mechanism offers maximum resistance to heat transfer, and that should the one we should be focusing on. The others are not that important. So, this is a good example of understanding the interaction between surface processes like reflection, emission, absorption, and what is happening in the gas between the surfaces, and how under certain condition the surface process may be more important, while in other situation the gas absorption may be very important. Now, so far we have dealt with radiative equilibrium. Now, radiative equilibrium is a special case, occurs only if radiation is the only process that is occurring and other processes are not important. But as most of you realize, in any real world problem, radiation occurs in conjunction with conduction, convection and other processes. So, radiative equilibrium is not something we encounter very commonly. So, you have to deal with problems where radiative equilibrium is not valid. So, I will take up a simple example of a situation where radiation is not in equilibrium, and this example, although very simply stated, has relevance to furnaces. Imagine a furnace in which heat is released at S dot watts per meter cube by combustion. Imagine a furnace in which there is combustion occurring, heat is released at the rate of S dot watts per meter cube. And for convenience, we will assume the two walls are the heat sinks. They are at the same temperature T1. Let us call them T wall. So, you have two walls at the same temperature, removing the heat while the furnace is where the heat is generated. Now, this is a very simple representation of a real furnace where heat is released by combustion, and the walls are the places where heat is removed by flowing water, which is your maybe a boiler, maybe the water wall of a power plant furnace or a superheater or some other place. So, this is a classic example of a standard problem in furnace or boiler design, and the basic formulation is that the rate of change of radiative heat flux has to be balanced by S dot. So, this is a formulation. So, this is a case where radiative equilibrium is not satisfied, because the divergence of the radiative flux is not 0. It is balanced exactly by the heat released by combustion. Now, this problem can easily be solved. First, we assume that you can write everything in terms of an optical depth kappa, which in this case is 0 to x a dx, where a is the absorption coefficient. So, this can be written as dqr dx plus S dot by a equal to 0, where a is the absorption coefficient of the gas. And as you recall, this becomes kappa, not x, sorry. Now, this you can integrate immediately to get qr is equal to S dot by a into kappa plus a constant. Notice that in contrast to the previous example where we dealt with radiative equilibrium, here qr is not a constant but varies with the optical depth. Now, we need information about constant, and this is most readily obtained by realizing the fact that the total heat released in the combustion chamber has to be removed from the two walls. By symmetry, the two wall flux QR 0 and QR kappa 0 have to be equal. And the total heat released S dot into L, that is heat released in the whole combustion chamber, has to be equal to this is equal to heat removed by the two walls. That is one requirement. And by substituting the values of QR at the two ends, you will get that this is 2 C plus S dot by A kappa 0, kappa 0 where is nothing but 0 to L A dx. And from there you can obtain a value of C. Okay. So, finally, we get expression for QR as nothing but S dot by A kappa minus kappa 0 by 2. And here you can see that at kappa equals kappa 0 by 2, QR has to be 0. And that is not surprising, because the heat released from the combustion chamber has to go out to both the walls. So, at the center of the wall, right in the center here, QR has to be 0. And that is emerging here clearly in the expression. Now, we have to solve for the temperature profile. So, our expression is for QR is S dot by A kappa minus kappa 0 by 2. This will be equal to, it will be same as what we did in the previous two lectures. The right hand side is essentially same as before, except that we will define our phi. So, phi we should recall is to be defined in this case, because the two walls are at the same temperature. So, we are going to define phi as T1 to the power of 4 minus T wall to the power of 4 divided by S dot by A. So, this is the definition which will ensure that the temperature profile has the same structure as what we did earlier. Here the basic driving force is the heat release of the ball. So, this is a proper definition. When you do that, the expression now for temperature profile becomes Now, you can differentiate this equation twice like before, and you will get and this you will recall will come from the Leibniz rule for the limits . So, you realize the fact that this term and this term, this term and this term are similar, except for the 9/4 term. So, we multiply this equation 9/4 and subtract, the two integrals cancel out, and we will be left with a very simple differential equation. So, this simple equation has some similarities to the equation we solved for the radiative equilibrium case. We integrate the equation, we get plus a constant. Now, this constant is very important, because notice that this phi is nothing but sigma t to the power of 4 minus d all to the power of 4 divided by s dot by a, and so let me just complete this equation. So, notice that at phi of 0 as well as phi of kappa 0, let us write phi of 0 first. This will be sigma T4 at the gas at the wall minus the wall temperature. Now, notice that this is not equal to 0, because this is a slip, because the temperature of the gas at the wall is not equal to wall temperature. So, this slip has to be calculated. Now, the accurate way of doing this would be to substitute this back in the integral equation and satisfy it at one location, say kappa equals 0, and you can calculate C. That you can do actually, it is a little tedious, but I will leave it to you to do that. I will do a different way, I will use a radiation slip condition. This is a shortcut, easy to do, and this you recall from the last lecture is nothing but this is what we obtained by Taylor series expansion for radiation slip, and in our case we know these two quantities. So, we can calculate the radiation slip as being equal to 1/4 kappa 0 plus 3/8. If you had used the Canal approximation and substitute everything back, you would have got so these two are not very different. This is almost 1/3, this is 1/3. So, the final expression for radiative heat transfer gas will be so this result, the general result you got here, and it has very interesting features which we want to recognize. You can see that both at copper equals 0 and copper 0 there is a slip which is can be quite large, and notice that in this case the slip never goes to 0. The slip is always there. It is very small when you are in thin limit, but as you go to thick limit this quantity does not go to 0. So, whenever there is radiation heat transfer, the slip exists always. So, this is the first important thing we see, and the other condition is in the optically thick limit, this quantity dominates over this quantity, and again the slip can be quite large. And so, this result differs from the earlier result we got for the radiative equilibrium, in which case we got the condition that radiative flux was with copper 0, and we saw that at copper is very large, the heat flux goes to 0, but here it cannot go to 0 because heat is being continuously generated inside the system, and this heat has to be transferred out. So, at no time, even the thick limit, the flux cannot go to 0, and as we saw, the flux is determined by the amount of as a matter of fact, we can easily see that S dot by L is the heat generated, and so half of it has to go this way, half of it has to go from the bottom plate. So, this is a requirement, and because of that there has to be a temperature gradient between the center and the wall, and this temperature gradient will go on increasing as you go to higher optical thickness. That is why the slip you can see is proportional to this one. As a matter of fact, we can take the case where K 0 is half T center line, and this will come out as this is K 0 by 2. So, we will get K 0 squared by 2. So, this result can be written in a more useful way as 1/4 K 0 squared 3 K0, it will be 3 by 4 plus K0 plus 3 by 8. And this is what shows clearly that the center line temperature goes on increasing as the optical thickness increases, because the gas must get rid of the heat generated inside the furnace continuously, whatever the optical thickness, and hence the temperature difference between the center line and the wall has to go on increasing. Let us see. The other interesting limit is K0 tending to 0, the thin limit. There we see that this center line temperature minus wall temperature become nothing but 3 by 2 here. So, this is the, in a sense, the minimum temperature difference that has to be maintained between the center of the furnace and the wall, even in the thin limit. So, this result is rather interesting, because the temperature difference is proportional to 3 by 8 into S dot by A, and of course, as limit A goes to 0, the difference in temperature becomes quite large. And again, one sees that the temperature difference between the center and the wall is proportional to the heat released, which is not surprising, and inversely proportional to the absorption coefficient, which might look a bit surprising, except that once you realize the fact that the efficiency of radiative heat transfer from the center line to the wall is partly determined by the absorption coefficient. If the absorption coefficient is quite small, then the efficiency of transfer becomes quite poor, and hence you need more temperature difference between the center line and the wall. So, from these exercises we have understood the role of internal heating, as in this case, or the role of wall emissivity, which you saw earlier in this lecture. So, we have done two problems in this simplest gray gas case, one involving radiative equilibrium and the other involving heat release in enclosure, which has to be removed from the gas by radiative heat transfer to the wall. And in both of them we saw that simple analytical solution provided useful information about the nature of the interaction between radiation and the boundary condition. Now, we took up the gray gas case first, because that is the case most convenient in terms of solving the problem. We realize the fact that the gray gas approximation is not a useful approximation for radiative transfer in gases in many real life situations, because most gases which absorb and emit radiation are not gray gas. In most gases, the absorption coefficient varies substantially with wavelength. So, due to this character of the absorption coefficient, very strong variation with, that is, in certain wavelength the gas can completely be non absorbing, and in certain other wavelengths the gas is strongly absorbing. So, for such a situation, it is rather difficult to define an appropriate mean absorption coefficient to solve the problem. So, it is better to recognize how to solve problems which are not gray. So, now we look at what I would call as a simple non-gray model. So, the simplest non-gray model involves accepting the fact that A lambda is not a constant. So, we take a very simple case where A lambda is different from 0 in a narrow range of wavelength. Lambda 1 to lambda 2. So, essentially what he is saying is A lambda is 0 for lambda below lambda 1, A lambda is 0 also for lambda greater than lambda 2, and is equal to a constant value for lambda between lambda 1 and lambda 2. So, there is a narrow region in which the gas is absorbing radiation, and outside this region the gas does not absorb radiation. This is of course a very crude representation of the real world, but it is a good teaching tool to explain how we take into account the non-gray characteristic of gas radiation. So, what you do is, in the case of this kind of non-gray gas, you calculate total radiative flux, which involves integral over all wavelength of the spectral radiative flux. We divide into 3 parts. In the first and the last part, of course, there is no interaction with gas. So, we can either write this as sigma T1 to the power of 4 minus T2 to the power of 4 minus integral over this wavelength where radiation is very important. Essentially, we have done the work of this is involves integration, these are integration really. So, this term is the term which is always easy to calculate, involves no gas radiation, but this term is pretty complicated, the second term, because we have to allow for the fact that radiative flux will vary in a certain narrow range in this wavelength. So, now for this problem we define the non-dimensional temperature somewhat differently, because non-gray gas. We take the temperature of the gas in the wavelength range of interest to us, that is lambda and lambda 2, and then and these bars are averages over the wavelength in which gas absorbs radiation. So, once you have done this, we can rewrite the radiative flux divergence terms in a simplified way. Before we do that, we would like to define a parameter which represents the, so now we write down the parameter called d, which represents the radiative flux in the wavelength range where the gas absorbed emits radiation. Compared to the so this can be thought of as the amount of radiation exchange in the absence of a gas between surface 1 and surface 2 in this wavelength interval delta lambda, compared to the radiation that is transferred from 1 to 2 at all wavelengths. So, this is crudely a measure of the radiation lying in the lambda range compared to the total. Now, you should recognize the fact that once we treat the gas as gray, this quantity becomes 1. For a gray gas, and for no gas, so with that we write down the expression for radiative flux, and as before we define Q star as QR so this is a definition between two parallel black plates, and with that we get the expression for Q star as 1 minus d plus 2d E3 of kappa plus d So, what you see here is that when you put d equals 1, that corresponds to gray gas, this term drops out, this term becomes 2, 1 and 1. This is identical to the gray gas expression that we had used earlier. So, extending the gray gas to non-gray gas was fairly simple, as long as you had talked about only one absorption band of the gas, and that interval is defined through the factor d. So, if d equals 0, there is no gas. So, Q star is 1, that we all know. In the absence of gas between the two plates, the rate transfer between two black plates is nothing but sigma T1 by T2 to the power 4, that is captured here. And the second thing is d equals 1, this term becomes 0, this is 2, this is 1, this is 1, we get back the equation for a gray gas. So, this is a generalization of the gray gas approximation, and again you can make the exponential kernel approximation same way. And solve the equation, differentiate twice, everything is identical. So, I do not have to do that. So, I will write down the final expression as so this expression again I want to remind you is similar to the gray gas expression, and I put d equals 1, once more you recover the gray gas limit. So, at each stage we see that the gray gas approximation is built into the solution. So, general solution now comes out as general expression for phi is this one, and you need two unknowns. They are constants and they are q star and d. So, once that relation between C and q star d is known, we have the complete solution to the problem, and we can show that q star is 1 minus d So, I want you to recall that this is quite similar to what we got a gray gas where d was equal to 1. So, I am got a slight difference here which you are very careful about. Notice that when d goes to 1, this becomes when d equals 0, of course, q star is 1, we know that result. Now, this is a very important result and we would like to understand and explain the result vis-a-vis result we obtained earlier for the gray gas. And the result that we obtain can be compared in various ways. And I will put down the temperature distribution. So, that is the expression for the temperature profile. And notice that this result is independent of d, that parameter which defines the fraction of radiation lying between lambda and lambda 2, that does not explicitly come in this equation. But of course, the q star, the radiated flux depends on d. And notice that in the limit as kappa 0 is much less than 1, phi of kappa becomes half. And that is most easily seen when you drop this term out and drop this term out. Phi equals 0. We just write this as half minus 3/4 kappa. Let me just redo this here. So, you can see this result is that the as kappa 0 becomes very large, this goes to 0, this term drops out, and as kappa 0 is very large, this goes to 0, this is half, okay. And so the gas temperature, as we saw earlier, is like this with two slips. And when kappa 0 becomes very large, your phi of kappa is 1 minus kappa by kappa 0. And here also you can see that this is a linear distribution which we saw earlier, and it is more like that, but there will be slip near the two walls, that is bound to occur. And so this essentially what we do is copper becomes very, very large. This term drops out, this is gone, this term drops out. So, this expression can be then used to be similar to what we had for gray gas. So, the temperature distribution between the two walls does not depend on whether it is gray or non-gray, but the flux expression was very different. It is a flux expression which gives it some unusual features which are different in the gray case, non-gray case. So, the key point is that as copper tends to infinity, Q star now tends to 1 minus D. This is a very important result, and we will take this up in the next lecture.